Okay, let's try a somewhat more awesome example. So the Apollo command module returned to Earth from the moon, and when it came into the atmosphere, this guy, this kind of thing, little window in there, woo! And so it's coming in here really fast. Hopefully the flames weren't looking like that, but we definitely had some shock waves coming off of it. Okay, but when it entered the atmosphere, it came in at a Mach number of 36. Pretty fast, right? Yeah. Okay, now we're going to make some calculations so we can figure out some things. So let's see here. What we want to know is what is the stagnation temperature right there on this module when my free stream temperature is equal to 360 Kelvin. Okay, so that's what I'm trying to figure out, because that is going to be the hottest point on this module, where there's the most ablation, where I have the most crazy chemistry going on, and all kinds of amazing particle physics happening at that point. So we want to figure that out. Now we're going to make one assumption. We're going to say that the ratio of specific heat is equal to 1.4. I'm just going to go ahead and tell you that it would not be. So this is going to be an underestimate in many ways, but we're using it because it's going to help us out. Now, we can go to the tables for this, but this is really, really high, and so this is one of those times where it's actually helpful, especially since it's only asking for one property, to just use the equations that I gave you last time. So in those equations, we have that our T naught over T is equal to 1 plus gamma minus 1 over 2 times the Mach number squared. Okay? So that's the big thing there. It's not a difficult equation. And so I can plug all that in. I get T naught over T is equal to 1 plus 1.4 minus 1 over 2 times 36 squared. So that's going to come out to be a value of 260.2, which is really, really, really hot. Because we can take that, we can do that now. So let's find out what T naught is. T naught is equal to, T naught over T is equal to 260.2. And therefore I can see that T naught is equal to 260.2 times T, which is equal to 260.2 times 360 Kelvin. Or in other words, would be 93,672 Kelvin, which is really, really, really hot. However, it's wrong. The reason is this equation up here is not for a chemically reacting flow. If we have a whole bunch of chemistry going on there, and in this case, like ionization of the gas, we're no longer going through air, more or less. We're now going through, some crazy ionized plasma thing, which acts very, very differently. So in real life, the temperature was still a balmy 11,000 degrees. But not 93,000. And also at this 11,000 degrees, air is a partial plasma. Okay, it's a partially ionized plasma. So it is no longer just air anymore. And just because I really like talking about it, if you don't know what a plasma is, that's simply when I have an atom, it's made up the protons and the neutrons. It has electrons going around it, and a plasma is simply when one of those electrons decides to leave. It's had enough, it doesn't like the positive attitude of the protons, they're always just ruining its mood, and so it goes off. And so when I no longer have that electron, I am now positively charged. I was neutral because there should have been 2 electrons here. I'll put the second one over here because it decided to hang out. But now that I've lost one of those electrons, I'm now positively charged. And so that's what plasma is. That's all it is. It's just atoms that are missing electrons. Or honestly, if they have too many electrons, it's also technically plasma. Or it's technically an ion. But plasma is typically when we have enough energy that it can just do this naturally. Like I can, by rubbing a piece of metal on my head or something else, steal electrons, so technically it's a charge. It's not plasma at that point.